All right, after that polynomial long division process, I'm guessing somebody's got to be interested in a shortcut. So that's what I would consider synthetic division to be. It's kind of a expedited way to accomplish the division that we need to. So in this video, we'll do probably 3 examples of synthetic division because moving forward, this is the process we'll tend to gravitate towards. And I'm just going to dive in right away with an example. We'll let this example kind of give us the hang of it, and then we'll do 2 more to build our confidence. So let's say that we were asked to divide this semi-long polynomial I'm jotting down here, 2x cubed plus 6x squared minus 5x plus 1, and we're dividing it by another polynomial, x plus 3. So what synthetic division does, and you can notate it different ways. So if you've already learned this process and your notation is a little different than mine, please don't worry, you can continue using it. But what I do is it's kind of like the division little house that we use for long division, but flipped upside down. And what we do is we place the coefficients of the terms. So 2x cubed, of course, has a coefficient of 2. 6x squared has a coefficient of 6. Negative 5x has a coefficient of negative 5, and then our constant term comes down as just 1. So what we're doing with synthetic division is we're just grabbing the placeholders for each term, but not the variable piece. So just the coefficients of each term. Now, outside the box, you would think that we're dividing by x plus 3, because we are, but with synthetic division, we don't include the variables. So instead, what we think about is, real quick, what makes x plus 3 equal 0? And it's that solution that we then divide by. So we actually use negative 3 outside of the box, not a positive 3. So be just a little careful with that part. All right, so I'm going to pause for just a second. Make sure the setup seems logical so far. Hopefully you can track completely with where each piece is coming from. Now we're about to embark on the process. And again, I'm going to do 3 examples. You can pause, back it up, watch again, whatever's going to help you. But I'm just going to walk through the process here and then again in 2 more examples. So now we're diving into the actual synthetic division process now that we have it set up. Here's how it works. We begin by just dropping the first number. So the 2 just drops down. Nothing's done to it. Now, and for every subsequent step, I'm going to take the number I just dropped and multiply it against the value out front. So 2 times negative 3 would give me the product of negative 6, and I place that now in the space in the second column. So I move to the second column and place the product of 2 and negative 3. Then I'm going to add down my second column. So what I'm walking through now is 6 plus negative 6, which is just 0. So I'm adding down that column to get 0. And then I repeat that multiplication step that we just did a minute ago. So now I'll be multiplying, I'm just going to get some space here, the 0 that we just got with the 3 sitting out front. So 0 times negative 3 gives us 0. So I place my 0 in my third column now. And now I'm just adding down column 3 to get the new number to place below. So negative 5 plus 0 is negative 5. Then again, I'm going to take that result and multiply it against the number out front. So negative 5 times negative 3, that sounds like a positive 15. Now I'm at the end of the rope here, so I'm just simply adding these results at the end. And this final number is the remainder. So just like with polynomial long division, we had a way to handle remainder. The number at the end indicates it's the remainder of the division process. Cool. So assuming you're watching the videos in order, the video right before this was actually the same exact problem, but through polynomial long division. So you can immediately compare and contrast the 2 methods. It's not enough just to leave the problem as it is, though, because we need to interpret what this answer really means. So we have a 2, a 0, a -5, and a 16. What do they mean? We began with a cubic polynomial, a degree 3 polynomial, right, back at the beginning of this problem. And we divided by x. So that implies that the degree is reduced by 1. So the 2 is holding the place of the x squared terms. The 0 is holding the place of the x terms. The -5 is just the constant terms. And the 16 is the remainder. And we have that special way, like we did last time, of writing the remainder. So to write our final answer in a more clear way, I'm going to say, just to repeat a little bit, that 2x cubed plus 6x squared minus 5x plus 1 divided by x plus 3 is equal to 2x squared. If you want to write the plus 0x, you can. It's not necessary, but I'll write it just so you see that placeholder. Plus 0x minus 5. And then for the remainder, we express it as 16 over whatever we divided by, which was x plus 3. So same answer we got in the last video using polynomial long division, just another way to look at it. Let's try 2 more before we call it quits. So if this first one didn't make perfect sense, we will continue clarifying with examples 2 and 3. All right, so next example comes to you as a division problem. We're going to immediately set it up in our little synthetic division box. I'm going to, like before, place the coefficients from the numerator in the box and place whatever makes the denominator equal 0 outside of the box. So in this example, our coefficients are 5, 3, and then our constant term is -2. And thinking through again, what do we put out front? I'm just going to grab the denominator. You don't really need to show work for this, but if you want to, you can. So I know that I'm going to place a -1 outside the box. And now we are ready to begin the process. So if you need to, pause right here, make sure you feel comfortable with this as the setup, and then I'm just going to dive into that same process we saw before. Okay, so here we go. We always begin by dropping the first number. Then we begin that multiplication process of the number at the bottom times the number out front. The result of that multiplication goes in the next column over. So we just multiplied 5 times -1 to get a -5. We're going to add those to get the value of -2 at the bottom of that second column. Anytime we've got the number at the bottom, then we multiply it by the number out front. So -2 times -1 makes +2. We always add, and in this case you can see that when we add -2 and 2, we get 0, and that is the remainder. Whenever you're stuck on how to interpret the answer, ask yourself what degree you began with. So we began with a 5x squared term. We divided it by an x term, so that means our solution will have an x term, a constant term, and then potentially a remainder. In this case, we don't have a remainder. So our answer could be expressed as 5x squared plus 3x minus 2 divided by x plus 1 is equal to 5, this 5 right here, 5x, and then minus 2. Remainder is 0, so I don't need to tag on a plus anything for that remainder term. Cool, so that would be the result of this synthetic division. We'll just tackle one last problem and then you can try some of these on your own. The reason I wanted to do a third example is sometimes we have what we call a missing placeholder. And all I mean by that is in this example, you'll notice we jump from an x cubed to a 4x term. So we understand that that implies there's really a 0x squared term in the numerator. So I don't want to just neglect it, but I want to use the placeholder of 0 when I set up my synthetic division. So just a small detail to watch out for that happens every now and then. So I'll just go through and circle my coefficients, and put them in my synthetic division box. So 1, 0, 4, and then our constant term is 10. And what would you think that we are dividing by this time? What number am I placing out front? So if you're saying 3, that is wonderful. Again, we're just thinking through what x value makes this denominator term 0. Now that it's set up, we can begin that process of dropping, multiplying. It's a very repetitive process, so once you've done it a couple times on your own, it will feel pretty intuitive. Begin by dropping the first value down. Then we're always going to multiply the value at the bottom against the value out front. In our case here, 1 times 3 gives me a 3 to place in the new second column. I then add down that column to get 3. I take the 3 we just found and times it by the 3 up front to get 9. Then I add down my third column to get 13. I multiply the 13 by the 3 out front to get 39. I add down my final column to find that my remainder in this problem is 49. So my answer is there, we just have to know how to interpret it. We always end with an answer that's 1 degree less than what we began with in the numerator. So just to clarify that point a bit, we began with a cubed term, so our final answer must begin with a squared term. 1 degree less than cubed is squared. So the 1 is the coefficient on the x squared term, the 3 is the coefficient on x, 13 is the constant term, and 49 is the remainder. So I'll take one more moment here to write this answer out in a careful way. So again, I need to take what we started with. Sorry, I can't remember. So it was x cubed plus 4x plus 10. And we divided that by, let's see, it was x minus 3. And our answer is 1x squared plus 3x. I'll just color code against the pieces from our work there, plus 3x plus 13, and then plus 49 divided by x minus 3. So that would be our final answer using synthetic division. All of these problems can be checked. The way you check is you would be multiplying your answer by what you divided by. If you feel up to that, for sure, have at it. If not, just make sure you're working super carefully through this process.